Okay, so on Wednesday we left off talking about, we talked about the tempering of carbon steel and talked about the four stages of tempering and how the diffusion of carbon out and the transition from tetragonal to cubic and the growth of epsilon carbide and cementite, right, and some properties. And now we have to think about what happens to the tempering process when you have other things in there, when you have alloying elements. All right, so we have to remember that generally our alloying elements are always going to shift our CCT curves towards the longer times, right? They're going to shift everything to the right. And some elements are strong ferrite stabilizers, others are strong austenite stabilizers, and some will have a very strong tendency to form carbides, and some do not, right? And so we have to think about this thing sort of all in a picture, right? In a whole picture, right? The first thing is that the more alloying we have in there, we shift our curve over, with the big exception of cobalt. We shift our curves over to longer times, right? Very good question, by the way, at this colloquium. you and Supriyo both asked, I think, really insightful, deep questions there.
My project is on that topic.
Okay. So all your alloying elements are going to shift the CCT curves to longer time, right? Which means it's easier to avoid the nose. You're going to have slower critical cooling rates, right? Easier to hit the Martensite, to get fully Martensite, right? Alloying elements also shift the Martensite start and Martensite finish down, right? Which means that the Martensite finish can now be lower than room temperature. So generally the higher the alloying, the more retained austenite you're going to have, right? So and then some elements, right? Aluminum, copper, silicon. These are not strong carbide formers, right? They're going to remain solid solution in the ferrite, right? And then other elements here are strong carbide formers, right? Molybdenum, vanadium, tungsten, right? Manganese, right? These are critical elements for tool steels and munition steels, and we'll talk a lot about their effect on effects during tempering, as they essentially tie up a lot of carbon into carbides, right? And so these are really going to play with the kinetics of softening during our tempering process, right? You can imagine what happens if we simultaneously diffuse the carbon out of the Martensite, but then we also nucleate nearly homogeneously a fine dispersion of carbides, right? Which are very potent strengtheners. Right? So everything gets tied together, and we have to think about everything, all of these different effects together. So the first stage of tempering isn't really going to be affected too much by the presence of the alloying elements, right? As a whole, though, the alloy steels are going to have a slightly higher hardness than steels with just equivalent carbon content, right? We've got additional solid solution strengthening that's happening, and we also are going to potentially have a finer grain structure than we would in a plain carbon steel, right? So at low concentrations, they're going to have the overall effect of slowing down the tempering process. Right? Especially not so much at lower temperatures, but at temperatures above 500 C or so, when these largely, particularly some of these very heavy solutes have sufficient mobility, diffusivity to take part in the tempering process, right? So we lose that para-equilibrium kind of idea that we talked about when we were forming the equilibrium sort of phases, right? So one of the biggest things we have to worry about is this secondary hardening that I had just mentioned. When you have strong carbide formers in there, they're going to nucleate a very fine dispersion of strengthening secondary phase carbide particles, right? And on tempering, you get a reduction and then an increase in hardness, right? This is very important for tool steels, right? You can imagine if you're using something as a cutting tool, right? Nowadays, we make most cutting tools out of carbide, but we still use high-speed steel in a lot of applications. But you can imagine if you're cutting something and you overheat your tool and it gets red hot, you want your tool to retain strength, right? And secondary hardening is a strategy for this, right? It's also very important in munition steels, right? When you can imagine high amounts of tempering at high temperatures for very short amounts of time, right? As you would get when you have a projectile moving through some media, right? Aerodynamic heating or impact heating or other types of things keep strength much longer. Okay, so if we have our strong carbide formers as before, this is just some notes essentially re-saying what I had just said before, but it lists what particular carbides you're going to be there. You get a lot of a mix depending on the concentrations. You can have a mix of homogeneous versus heterogeneous nucleation, right? Heterogeneous nucleation in this case is going to be mostly happening on dislocation structures, right? Right. The big ones: molybdenum, vanadium, tungsten, chromium steels at higher chrome concentrations, right? This becomes a little tricky because higher chrome is also a very potent austenite stabilizer, right? Remember how we said chrome is kind of an anomalous one, that at low concentrations it's a spherite stabilizer, then at high concentrations it's an austenite stabilizer, right? So you can get secondary hardening. Chrome also participates in secondary hardening, but you're kind of limited in the range where you're going to get a lot of Martensite, right? If you have too high of a chrome concentration, you're going to have huge amount of retained austenite and not a lot of Martensite. So the amount of secondary hardening you're going to get is it becomes very complicated. Yeah.
So we take austenite, we get Martensite?
No. So when you cool down, right, all of your austenite is going to either change to Martensite, provided you miss the nose, right? We hit our critical cooling, right? If we could cool down low enough, we would get all Martensite, right? But if our Martensite finish temperature is too low, right, we're still above that at our quench temperature. we're going to have retained austenite. Right? Okay. I know that alloying stuff is kind of boring, right? But you have to go through the effects of these. Okay. So silicon is important because it dissolves, destabilizes the dissolves. I'm going to set it backwards. Dissolves in the epsilon carbide and stabilize it. Right. So typically during stage 2 and 3 of tempering, we transform the epsilon carbide to cementite. Silicon will stabilize the epsilon carbide, and it will prevent the formation of cementite and retard that softening. And so it acts as in this sense, it acts as a strengthener in the tempered state, right? It won't soften as quickly. Yes. Yeah, at higher concentrations, right? So this is only, you get 1 or 2%, right? If you go too high in silicon, yes, you're going to promote the formation of graphite, right? Alloy design, if you haven't figured it out yet, alloy design is amazingly complex, right? And we have all these kind of trends and rules and thermocalc, right, to try and calculate the phase diagrams, but they're notoriously bad when you have 6-element cocktails, right? All of these things come together means that alloy design is a ton of trial and error, right? You can get something in the ballpark a lot of times, and then small tweaks, right? I mean, this is why super alloy development is still such an important thing, right? And this is why I think high entropy alloy development or multiple principal component alloy design is going to be a thing for the next 30 years, because the space is huge and the rate at which you can physically explore things, either computationally or realistically, is very small, right? And where, for example, where this line is going to depend not just on the silicon content, but all the other alloying elements that you have in there, right? So sometimes you see things that appear to be completely contradictory. And it's not because of the effect of the primary thing you're talking about. It's because in this particular steel, I have 5 other, or this particular super alloy, I have 6 other elements that are messing with phase boundaries. And so keep that in mind, right? This is why I say a lot of this stuff isn't kind of important to memorize, right? It's not important to know that exactly that 1 or 2% silicon, right? But if you know the general strategies, the big picture stuff, right? Almost everything's going to shift to longer times, right? These are my potent carbide formers. What's going to move my Martensite start, Martensite finish? Those are the kind of important things to know, right? The crystal structure of epsilon carbide, no. What's the maximum solubility of silicon in epsilon carbide? Who cares? Right? Someone does. But these are things you can look up. Okay? So nickel, right? Nickel is pretty much there as a solid solution strengthener because it's not a strong carbide former. Yeah. Sorry.
I have a question. Now we have a thermocalculator that allow us an alloy by design approach.
Yeah.
Alloy designing, but steel has been around for such a long time. I'm just wondering how people came up with design ideas when there was no.
Trial and error. Tons and tons of trial and error. Right? It used to be in the 50s and 60s, experimental measurement of a phase diagram was like a PhD topic, right? You would just make thousands of samples at different concentrations and heat them and quench them and basically do 5 years worth of work and plot out a binary phase diagram, right? Now binaries are for the most part, pretty easy to calculate, right? In the future, I think alloy design will eventually get there computationally. But for the most part, a huge number of these compositions are really guided by some basic principles, right? Things like Hume-Rothery rules and some experimental observations about general kinetics, a lot of intuition and experience, and luck, right? I mean, stainless steel was invented completely by accident, right? High chrome steels were designed, eventually a failed test for something else, and then someone was like throwing out a box of stuff 5 years later and noticed that everything in the box had rusted except this one sample, right? So a huge amount of luck and trial and error, right? Okay, so nickel, basically solid strengthener. It's not a very strong carbide former. Manganese is segregates to the cementite, right? And so it's essentially, it is going to resist cementite coarsening. It diffuses into the cementite faster than other refractory elements, right? It's still slow relative to the diffusion of. It's still slower than the kinetics of the cementite, the carbide formation. The
cementite is only iron or metal.
You have, yeah.
And manganese, it is slower than iron, then it will return.
Yeah, it's. Let me think about this. Manganese is going to. Right. It's much slower than tungsten, vanadium, and to grow the cementite. Right. Yeah, sometimes seems kind of off with this argument. Let me go back before I say something dumb. I have to be careful about that, right? I don't want to. Let me look it up. This is. Yeah, you keep me honest. As I was saying it, I'm like trying to figure it out. I worked through it when I revised myself on these slides a couple weeks ago. I made sure I had everything straight in my head, and since then I've it's not straight right now, so I have to go look. All right. Generally, these carbide formers will help maintain tetragonality, right? They will because they want to be near the carbon. They'll slow the diffusion of the carbon out of the Martensite, right? And so the tetragonality of the martensite stays around longer. So they will retard the softening on tempering, right? So
low temperature is supposed to be.
yeah, so the plain carbon steel, right, is martensite's BCT, right? Without any other elements in there, carbon diffuses very quickly, right? So even at 300 C for half an hour to an hour, you will diffuse enough carbon out to lose tetragonality, right? Strong carbide formers, right? They're also heavy refractory, very slow diffusers, but the carbon wants to stay near them, right? And so you're slowing the diffusion of carbon out of the martensite, and you maintain your tetragonality higher. Maintain your tetragonality, right? For longer, right? And in plain carbon steels, right, you've got this coagulation of cementite particles that come together, right? They form essentially a bigger cementite particle rather than a fine dispersion. You have elements, silicon, chrome, molybdenum, vanadium. These also prevent the coalescence of the cementite particles, right? So these will enhance hardening and reduce softening, right? Greater than the effect they would have if they were just in solid solution, right? And then we have delayed coarsening, right? Because these will strongly form their own carbides, right? And they'll delayed coarsening of cementite, right? So instead of getting coarse cementite particles, you get a fine dispersion of carbides of these elements, right? Right. And this is basically just a couple of those trends illustrated, starting with a iron 10 nickel, right? So iron 10 nickel, this is basically just solid solution strengthening, right? You add some carbon, you get martensite formation, right? The strength on quenching goes up due to martensite, and then you get a large fall on tempering, right?
Or x-axis the tempering temperature.
What's that?
X-axis the tempering temperature.
Yeah. So if it's just solid solution strengthening with no martensite, you have no effect on tempering, right?
Yes.
Right. So then, as quenched, if we have carbon in there, now we've got martensite formation, and then we have softening on tempering.
What is the reason for it?
It's a little bit of aging, right? But right then, if you have cobalt, right? Remember, we said cobalt doesn't shift the curves at all, right? So essentially, the martensite level is still the same. So in the as quenched condition, it's going to be the same, right? But now we have additional final hardening due to the solid solution strengthening of cobalt, right? Cobalt's not a carbide former, right? If we add some chrome, right, we now have a continuous hardening on tempering due to the formation of chromium carbide, followed by a softening. Then if we add molybdenum, we get a very strong secondary hardening, right, from molybdenum carbides that form, right? So an example, something like this, I think is a good kind of exam question, because it doesn't necessarily require you to memorize what all of these different things do. Right? Going the inverse, saying sketch the difference in curves between a iron nickel carbon versus the other, that's prognostication, right? But having the data, right, and being able to make a credible statement about what's happening as you change the composition, right, is a much more realistic type question that I would think is important. Yeah.
Presuming that the quench rate remains the same, as I increase the alloy elements in the steel, and I'm not depressing the martensite finish temperature, so should I not expect that the amount of austenite is kind of different in the alloys? So, I mean, I'm just wondering why the as quench.
Yeah, we don't know what the quench temperature was or the cooling rates on these. Right? We assume it's faster than the critical cooling rate, right? But we don't know what the final quench temperature is, right? So I think, well,
should be.
You can do a cryo treatment, right? Right, and get down below, right? And then room temperature is kind of a tempering, right? But your kinetics are so slow, right? Given very long times. But, these are held at temperatures much higher. Essentially, these have to be standardized in some way, shape, or form, but I don't know the details of how that was, right? But you're right. Especially chrome and molybdenum are really going to lower the martensite finish. They're also going to push the nose over, right? So you'd have a much slower possible critical quench rate. Right. The idea is trends, right? Details are not as important, right? So these are more slides these are the slides I put together on secondary hardening before I discovered Professor Kumar's heat treatment kind of stuff. So there's some additional information. So one way of normalizing data is this, what we call this Holloman-Jaffe temperature, right? Sometimes just called a tempering coefficient, right? And it's a way of rescaling time and temperature for tempering. So anything that has the same coefficient should have the same resulting microstructure and degree of softening, right? And so when you look in the tempering literature, you'll see a lot of things plotted against P rather than time as a way of normalizing quench temperature versus time at quench, right? Or time at, not quench temperature, tempering temperature versus time at temper, right? Okay. And then nucleation and growth of the alloy carbons. This is basically as we have said before, right? We have nucleation heterogeneously on dislocations in the martensite substructure, right? Remember, there's a lot of plasticity that accompanies martensite formation, and if the carbon content's low enough, you have slipped martensite rather than twin martensite. So you have a very high dislocation density, right? So you can nucleate heterogeneously on the dislocations and still have a relatively homogeneously spatial dispersion of carbides, right? You're still going to nucleate at grain boundaries, and from any existing cementite particles that you have are natural places for nucleation of the alloying carbides, right? And so I mentioned Widmanstadt and cementite before, right? And this is just showing some of these features in the micrographs, sort of at tempering, right? where you have different conditions, different nucleation conditions at different temperatures. Right. Right. Vanadium carbides tend to form these small coherent platelets, right? Chromium, you get a range, two primary carbides, but you also have some others, and they're going to have different degrees of stability. Again, these are sort of more for information rather than things I expect you to sort of know, right? So, this is kind of a benefit of chrome vanadium steels, right? You get these fine platelets that form early. They nucleate heterogeneously on dislocations. They give you strengthening at lower temperatures. They coarsen rapidly at higher temperatures, right? But if you have chrome in there too, you get higher, these very thermally stable chrome 23C6 oxides, which helps you maintain strengthening at higher temperatures than just the vanadium alone, right? Again, it's not something kind of expect you to memorize, but just kind of an example of how you can think about alloy design, right? You have things that are going to nucleate and grow different phases at different times, right? Can we find a strategy where things disappear in one and come in the other, right? It's like you ever, I was lucky enough when I bought my house in Worthington, the previous owner was a master gardener, right? She was retired and spent literally all day, every day out in the garden. But she had things staged so beautifully that as one thing was dying off, new things were coming into bloom. She had the time, like it staged beautifully. So for the first 4 years we owned the house, there was always something beautiful happening in the garden, right? Everywhere. But now all that's unfortunately gone because I have zero idea how to make. Neither my wife have neither the time nor the skills to maintain that, right? So in year 5, something bizarre happened, right? And it all completely went to hell. The balance over time got off a little bit, right? It didn't thin things out the way we were supposed to be or fertilize something the way it was supposed to be, right? But it's this alloy design is the same kind of thing. You've got all these little effects, right? You're trying to put them together so that over the range of conditions that you think you're going to have, you have all of the right pieces in place, right? Okay. So this is just comparison of alloying steels versus plain carbon steels, right? With respect to impact strength and tensile strength in the tempered condition, right? And generally you can see, look, I've got a higher tensile strength, right? But we also have, even though we have higher strengths, we also have stronger, a higher energy absorption, right? So in the alloy steels, we get better strength in plain carbon, but we also have better ductility, right? More or better toughness. Ductility is not exactly the word I wanted there, but we have higher toughness, right? So this is really a driving force for why people put more alloying elements in here. All right. This is again kind of a secondary hardening, right? If we can utilize secondary hardening properly, we can get very good ductility, right? At tempering between 500 and 700. And if we can form the stable carbides, we're good, right? So in the beginning of class, I mentioned Mar-aging steels, right? And interstitial free steels, right? Mar-aging steels have very low carbon in them, right? Therefore, they really make use of secondary hardening, and essentially the secondary hardening and the carbide precipitation essentially eats up all the carbon that you have in your alloy, right? And so these are typically used for high strength applications, right? And a lot of munition steels started life out as Mar-aging steels, right? They were another generation on top of these, right? But basically, the whole strategy for these is to make use of secondary hardening. We don't have any very much, if any, carbon in solution anymore by the time that we're done, right? So essentially, these are going to behave much more like a precipitation strengthened aluminum alloy than a steel, right? Because we don't have, well, it's still BCC, it's still ferrite, but, right, in principle, we can think about them in the same sort of way because we don't have all these interstitials, right? Okay. Is that clock right? No, that's not right at all. No, it is right. Wow, okay. Okay, so there's a couple things, pitfalls that we do have to worry about, right? And there are sort of known temperature ranges that when you're tempering, you want to stay away from. So if you look at tempering versus impact strength, right, we see the impact strength goes up until we get to about 250, then it drops back down, then it goes back up, and then around 500 it drops back down again, right, where we embrittle our steel in certain temperature ranges. Right? So there's have unfortunately confusing names. We have tempered martensite embrittlement and then tempered embrittlement. And I always get them mixed up and I have to look up which one is which. Right? Okay. So tempered martensite embrittlement is the lower temperature, right? It's 260 to 370, sometimes called 350C embrittlement. One-step embrittlement or irreversible embrittlement, right? This irreversible embrittlement is a very confusing name, right? And because to me, irreversible embrittlement implies once it's embrittled, you can't fix it, right? But what it really says is if you heat it up above the temperature, it goes away. And then if you cool it back down, it doesn't come back, right? But you'll see it in the literature sometimes called, especially in industry, things, not so much in the scientific literature, but in more industry-driven things, it'll be called irreversible embrittlement. If you look in the AIST, if you're a member of Materials Advantage, you get the AIST magazine, right? If you look in there, you'll see this irreversible embrittlement sometimes, okay? So this is something that really affects a wide range of steel compositions, right? And so you have in the range where we're removing epsilon and forming cementite, in this range, the cementite will tend to form a film at the grain boundaries, right? And if you have a continuous cementite film near a grain boundary, of course, that becomes an easy crack propagation path, right? If you go above it, that cementite, the film disappears, and if you reheat it again to that temperature, that film doesn't come back. That's why it's called irreversible. Irreversible hardening. If you have alloying elements, right, not very common, right? We tend not to use phosphorus too much as an alloying element. But anyway, if you have them in there, it will prevent the film of cementite and will preserve the strength, and you don't end up with this tempered martensite embrittlement. Silicon is much more useful because it retards the formation of the cementite and keeps the epsilon for longer, so you don't see tempered martensite embrittlement if you have 1 or 2% silicon in your steel. Yeah.
So in all steel we have this improved gel.
Yeah, for the most part, right?
So when we are high curve, it's possible.
It is.
When we are high cold, now we can get cementite down.
It's just you're dissolving the epsilon, right, and nucleating cementite, and the grain boundary is and this temperature range is a much better nucleation site.
After tempering.
This is during tempering, right? Right. So this is, yeah. So we're coming from austenite, martensite. This is during the tempering process, right? If we temper at a lower temperature for a longer time, we have good toughness. If we temper for a higher temperature at a shorter time, we have good toughness. If we temper in this 250 to 300 to 400 range, we have very bad toughness, because in that range we're growing cementite at grain boundaries.
But this one, like, once you go to higher temperature and come back, the problem is fixed, right?
The problem's fixed, yeah, because then you've nucleated cementite other places.